right, so we just finished our notes on 5-6, which really takes some concepts from chapter 4 about graphing a line, and then kind of meshes it with what we've been doing in chapter 5, which is all in inequalities. So in chapter 5, when we graph the line, we're not saying what equals that equation, but more so less than or greater than that equation. So the line itself represents all the ordered pairs that make the equation true. Then the shaded region are all the ordered pairs that make the inequality true. You're drawing a picture of the solutions, kind of like the way that we drew a picture of the solutions with the number line. It's really the same concept, but now we're just dealing with when we draw these solutions, instead of saying x less than 3, we would say it was open circle at 3 and to the left. Well, now we might have solutions where there's an x and a y. And so open circle on the number line is the same thing as a broken line on the graph. So if you look at graphs B and C there, they're broken. We do not include those ordered pairs as solutions. The only ordered pairs that are solutions are in the shaded region. So it's just taking the concept of the number line onto the coordinate plane. So the first 4 problems match each inequality to the graph of its solutions. One part of this, you can use some process of elimination. If you look at number 1 there, number 1 is just less than. And so when I see that less than sign, I know it's broken. Okay, so all of a sudden, I know that A and D are not my choices. So number 1 could be B or C. The way it's written right now, it's kind of confusing. So what I would suggest doing is rewriting that as an equation just to get the equal sign part, just to see where the line is, and put that in slope-intercept form. So to review slope-intercept form, if we can get the numbers to look like this, get the equations in this form, this is where we begin our graph. Nothing's changed from graphing, and this is what we move. Remember, when we move, we rise, we go up and down first, and then we run. So to get this to look like that form, I'd have to add 2x to both sides. And I'm just going to squeeze that over here. Y equals 2x plus 2. So that particular line, I'm looking for a y-intercept of 2. Well, I'm not even going to look at graph A, even though graph A has a y-intercept of 2. I have to have a broken line. So I'm going to go to B. B also has a y-intercept of 2. Let's see if the slope matches. Up 2 over 1 or down 2, 1 to the left. I think we found our winner. Number 1 is B. So I'm going to let you guys kind of figure those out. But it does show you if you've got to get the equation in this form in order to graph it. Okay, that's how we graph. So if you look at numbers 2, 3, and 4, you might have to do some rearranging there. Moving on to the next section. So the next section is just trying to understand what a solution is. We can have several numbers, just like when we graphed on the number line, it goes all the way to positive or negative infinity. So do these. So we're wondering, would these, if we were to graph it, would they be in the shaded region, meaning the solutions? So we're just going to do some quick little tests of each of these ordered pairs. So the first ordered pair I'm going to check is 4, 3. I'm wondering, is it a solution? So this is my x, this is my y. I'm just going to simply plug it in to the inequality and interpret what the results. So 3 times 4 plus 3, is that greater than or equal to 6? I'm questioning that. And then 3 and 4 make 12. Is 12 plus 3 greater than or equal to 6? Is 15 greater than or equal to 6? I'm questioning this. 15 is greater than 6. And so I would include 4, 3 as a solution, meaning if I were to graph that, 4, 3 would be in the shaded region. Okay, without having to graph it, that's what we're doing here. For negative 2, 4, so let's look at negative 2, 4. Here's my x, here's my y. I'm going to do the same thing. I'm going to plug them in. 3 times negative 2 plus 4, is that greater than or equal to 6? I don't need to see the work in between. I mean, I think it's easier than plugging it into the calculator. But if you just plug in everything on the left-hand side and get the answer, so if you plugged in 3 times negative 2 plus 4 in your calculator, write it down so I can see what you're plugging into your calculator. And then you get -2 greater than or equal to 6. That's false. So because that's false, we're going to cross it off and say, no, that would not be a solution. We're over here, I could have put a T for true, right? 15 is greater than or equal to 6. So that is a solution. We're looking for all the solutions that would be in that shaded region. That's what the shaded region represents, the answers to this inequality. Let's go on to the next inequality. So -5, -3, I'm just going to show my work over here. 3 times -5 minus 3, because plus a negative, is that greater than or equal to 6? So when I do that calculation, 3 times -5 is -15 minus 3. I get -18 greater than or equal to 6. That's false, right? You can put the little line through it saying not true, right? You can put false. But in the end, it's not a solution, so it would not show up in the shaded region if we were to graph that inequality. And then the last one is 3, -3. So I'm going to do it one more time. You're going to show all the work. This is my x, this is my y. You plug them in. 3 times 3 minus 3, is that greater than or equal to 6? That's 9 minus 3 is 6, greater than or equal to 6. Yes, this is true because of that line. That line means equal to, so we're allowed to include it. So the other solution that would be in here is 3, -3. You're not guaranteed any of them to work. All of them could work. There's no rhyme or reason. It's not, oh, one works and the others don't. You got to try every single one. Pretty easy concept here, but it's trying to illustrate the idea of there's multiple answers and what a solution means. It means when you plug it into the inequality, it gives a true result. That's what a solution to an inequality is. So continue the same way for number 6. Give you a little hint on number 7, even easier, because in number 7, there's no inequality to plug it into. Plot the ordered pair. So if I plot -1, -3, -1, -3 is an ordered pair down here. The fact that it's sitting down there and it's not shaded tells me it's not a solution. And trying to drive home the idea of what a solution is, that the shading represents the ordered pairs that work. Okay, so 7, I really don't need to see work other than plotting the points on the graph and circling it, saying yes, it's included, or crossing it off, telling me it's not included. Okay, if we can move to the back, on the back page, we are graphing and doing our own. So we're doing everything that we kind of already talked about. One more time, let's just put this up at the top. Your equation needs to look like this, or your inequality needs to look like this. I usually switch them to an equation just to get the boundary line, and then I do a test to determine shading. This is where we begin our points, our graph, and this is how we're going to move from one point to the next. Okay, so let's go ahead and do number 9. Number 9 is already in this form, y equals mx plus b. My m value or my slope is 1. I can put it over 1 because there's 2 motions there, and then my y-intercept is -5. So I'm going to begin at -5 on the y-axis. Put your beginning point, and then you're going to move the slope. You're going to go up 1, 1 to the right. And then you're going to connect and extend those. So that's the boundary line. That is all the ordered pairs that make that equals. Okay, we're going to include them because of this line underneath. We're going to keep that a solid line, so we don't have to break it. I always break it after I graph it, so it's going to be a solid line. And then now I need to check points above it or below it. You can't be true in both regions. The line creates 2 different regions, region above and region below. One represents greater than, one represents less than. And so we got to test a point. The easiest point to test for shading is 0, 0. The only time you cannot use 0, 0 is when the line actually goes through 0, 0. But I'm going to put a little X there, and if in this particular case, 0, 0 is above my line. So when I check 0, 0 to see if it's a solution, just like we did on the front, we plug it in. If 0, 0 is a solution, that means every point above the line is a solution. If 0, 0 isn't a solution, then that means all the solutions are opposite. You shade true. You don't have to keep plugging in points. One point will tell you everything you need. You just got to do a little thinking. This is my little check mark. of showing what I'm checking. I'm using 0, 0. So I'm going to plug in 0 for X, 0 for Y. The nice thing about 0, 0 is they're just easy to work with. So I'm using this inequality and bringing it down here. So the Y value is 0, greater than or equal to, we're checking, we're questioning, is 0 greater than or equal to 0 minus 5? Or if I clean that up, is 0 greater than or equal to negative 5? And the answer is yes, that's true. So if that's true, that means this is a solution. If 0, 0 is a solution and it's above the line, all of the ordered pairs above the line are solutions, so we shade. If we got false, then we would shade the opposite of where 0, 0 is. It is not greater than is above and less than is below. It is not greater than is true or above is true and below is false. It changes every single time. You have to do this test and you have to think it through. Okay, let's go on to a more complicated one. Let's go down to number, let's do 13 together because there's so much going on. You're also going to have to fix this one. Okay, that one's out of order, so you're going to have to do some cleanup, but I think 13's cleanup is just a little bit more difficult. So I'm going to take this inequality, and while I'm cleaning it up, I'm going to leave that alone. I'll come back to that when I go to check my point for shading. I'm going to change it to equals just to get the line, because technically, guys, the line is when it's equal. It's the equation. So I'm just going to change the inequality to equals just to get my y equals mx plus b. This looks nothing like y equals mx plus b, so I got a lot of work to do. I'm going to add the x over. I can call that 1x. So that leaves me with a negative 2y equal to, I'm going to let x cut in front. The 1x goes out in front, and then the minus 3. It's getting closer. I got to get rid of that negative 2. So I'm going to divide this by negative 2, the 1 by negative 2, and the negative 3 by negative 2. In doing that, I get y equals negative 1/2 x. There's my slope. And then the negative divided by negative makes a positive. And I'm just going to leave that as 3/2. In our head, though, on our calculator, we can think of 1.5. So our beginning point is 1.5. So we are 1.5 units up on the y-axis. Just put it right smack dab in the middle of that line, right between 1 and 2. And then when we count our slope, when we count down 1, I'm still going to be at the half mark. So there's my down 1. And then I have to go 2 to the right. And then down 1, 2 to the right. I could also go up 1. I'm still in the half. 2 to the left. All right, I have enough to connect. So I'm going to connect and extend that through my graphing area. Notice that the inequality doesn't have that line. So that means these ordered pairs is when it equals negative 3, but we can't include when it equals negative 3. It's like open circle. So broken line is the same thing as open circle. We can't include them. That's our little visual to the readers. Mathematically, people that understand math say, oh, okay, we're not including the ordered pairs on that line. Now we need to check for shading. So when we check for shading, we pick a point not on the line. I can use 0, 0 again. This time 0, 0 is below it. So I'm just going to show my little work down here that I'm checking 0, 0. I'm going to use this original inequality here. And so when I put that down here, wherever I see y, I'm going to plug in 0. Wherever I see x, I'm going to plug in 0. And we're wondering, is all that junk greater than negative 3? Negative 2 times 0 is just 0. Minus 0 is 0. This whole left side simplifies to 0. Is 0 greater than negative 3? That is true. 0 is greater than negative 3. So where 0, 0 is, that's a solution. It's below, so that means all of the ordered pairs below would work. If you don't believe me, try some more points. If you don't believe me, try the points in the opposite region and you'll get a false result. Okay, I didn't get any false, but false just means you shade opposite. Okay, so 12 needs to be fixed. Number 11 looks pretty good. I want to go back up to the top here just really quick to talk about a couple of these other ones. Number 10 is missing the b value, so add it. You have it. But I'm going to tell you, you're going to go through the origin, so you can't use 0, 0 there. And number 8, one variable, one motion. Okay, make a table of values where all your y values are negative 1. This will help you create your line. because it's either horizontal or it's vertical. I'm not going to help you with that one. You guys can try that one on your own. Okay? Due at the end of the hour. Good luck.